Every time we use artificial intelligence, somewhere in the world a data center is working. Behind the digital world, there's a physical energy system: servers, cooling, electricity, transmission lines, and power plants. As AI becomes larger and more widely used, the question is no longer only about better algorithms. The question is also, where will the energy come from? Renewable energy is growing quickly, but wind and solar are variable. They do not always produce electricity exactly when data centers need it. This is where the underground becomes important. Deep geological formations may act as giant natural storage systems for hydrogen, CO2, heat, and energy flexibility. So today we ask a big question. Can the underground help power the AI era? AI feels invisible because we use it through phones, laptops, and cloud platforms. But the infrastructure is very real. Data centers consume electricity continuously, and they also need cooling systems to remove heat from servers. This means AI is connected to electricity demand, grid stability, and energy security. When AI demand increases, the power system must respond. It must provide reliable electricity not only for a few minutes, but 24 hours a day. This is why AI is becoming an energy problem. The future of AI depends not only on chips and software, but also on clean, stable, and scalable energy infrastructure. Renewable energy creates a timing challenge. Solar power is strong during the daytime, but AI data centers continue operating at night. Wind power can be strong in one season and weak in another. Electricity demand, however, does not wait. This mismatch between energy production and energy demand is one of the biggest challenges for clean power systems. Short-term batteries can help for hours, but for longer periods, days, weeks, or seasonal balancing, we need other storage options. This is where underground storage becomes attractive. The subsurface can potentially store large amounts of energy over long time scales. Surface batteries are very useful. They respond quickly, stabilize grids, and support renewable energy integration. But they are not always enough for long-duration or seasonal storage. For example, if we want to store excess renewable energy from spring or summer and use it in winter, the required storage capacity becomes enormous. Building all of that storage only on the surface may be expensive and difficult. Therefore, the future energy system should not depend on one technology alone. We need a portfolio: batteries for short duration, hydrogen for long duration, CO2 storage for climate mitigation, and geothermal energy for clean heat and power. The deep earth is not empty. It contains porous rocks, saline aquifers, depleted oil and gas fields, fractured reservoirs, and hot geological formations. These underground systems can act as natural energy infrastructure. Some formations can store hydrogen. Some can permanently store CO2. Some can provide geothermal heat. And all of them require careful engineering. The idea is simple but powerful. Instead of building all storage above ground, we can use suitable geological formations as large underground vaults. But we must understand pressure, fluid movement, trapping, leakage risk, and long-term behavior before deployment. Hydrogen is a promising energy carrier. When renewable electricity is abundant, we can use it to produce hydrogen. Then hydrogen can be injected into underground reservoirs and withdrawn later when energy demand increases. This is especially important for long-duration and seasonal storage. Hydrogen can store energy for weeks or months, supporting power generation, industry, and transportation. But underground hydrogen storage is not simple. We need to predict how hydrogen moves, how much can be recovered, how much cushion gas is needed, and whether the reservoir can maintain deliverability over repeated injection and withdrawal cycles. That is why simulation is essential. CO2 storage is another important underground technology. In this process, carbon dioxide is captured from industrial sources, compressed, transported, and injected into deep geological formations. The goal is to keep CO2 underground safely for very long periods. This helps reduce emissions from hard-to-abate industries such as cement, steel, hydrogen production, and chemical manufacturing. CO2 storage is not just disposal. It is engineered climate infrastructure. We must understand where the CO2 plume moves, how pressure builds up, whether the caprock remains secure, and how trapping mechanisms improve long-term safety. Geothermal energy uses heat stored inside the earth. In many systems, cold water is injected into hot rock, absorbs heat, and is produced back to the surface as hot fluid. This heat can be used for electricity generation, district heating, or industrial processes. But geothermal systems must be managed carefully. If cold water moves too quickly from injection well to production well, the system may experience thermal breakthrough, reducing long-term efficiency. Simulation helps us design well spacing, injection rates, and sustainable operation strategies. So geothermal energy is another example of how the subsurface can support clean energy. Underground energy systems are powerful, but they also involve risk. When we inject fluid underground, we change pressure. Pressure changes can affect fluid migration, caprock integrity, and fault stability. If pressure becomes too high, it may increase leakage risk or reactivate faults. This is especially important for CO2 storage, hydrogen storage, geothermal energy, and wastewater injection. So the key message is we cannot inject blindly. We need prediction, monitoring, and safety limits. Reservoir simulation and geomechanics help us understand how pressure and stress evolve underground. The future is not only physics-based simulation, and it is not only artificial intelligence. The strongest workflow combines both. Physics-based simulation gives us trust because it is based on conservation laws and rock, fluid physics. AI gives us speed because it can learn patterns from many simulations and make rapid predictions. Monitoring gives us reality because field data show what is actually happening underground. A digital twin connects these pieces. It updates the model with new data, forecasts future behavior, tests scenarios, and supports better decisions. This is the intelligent underground energy system of the future. A common question is, if we inject CO2 underground, how does it stay there? The answer is trapping. Several trapping mechanisms work together across different timescales. First, structural trapping occurs when CO2 rises and is stopped by a low permeability caprock. Second, residual trapping immobilizes CO2 in pore spaces as disconnected bubbles. Third, dissolution trapping occurs when CO2 dissolves into brine. Finally, mineral trapping happens when dissolved CO2 reacts with minerals and becomes solid carbonate minerals. This means CO2 storage security improves over time. The plume must be monitored, but the physics of trapping can make storage increasingly stable. Underground hydrogen storage is different from CO2 storage because hydrogen is not only injected once. It is cycled. When renewable energy is abundant, we produce hydrogen and inject it underground. During high energy demand, we withdraw hydrogen and use it for power generation, industry, or fuel. This cycle may happen daily, weekly, or seasonally. The reservoir must maintain pressure and deliverability. Cushion gas may be needed to keep enough pressure inside the reservoir so that hydrogen can be withdrawn efficiently. Simulation helps us answer practical questions. How much hydrogen can we store? How much can we recover? And how performance changes after many cycles. In underground energy systems, pressure is often the master variable. Pressure controls injectivity, storage capacity, plume migration, fault stability, and operational safety. When fluid is injected, pressure rises near the well and spreads outward. In many cases, the pressure footprint is much larger than the actual gas plume. This is very important. Even if CO2 or hydrogen stays near the injection area, pressure can affect a much wider region. Therefore, safe design requires pressure management. We must monitor pressure, define safe limits, and optimize injection or withdrawal so that underground storage remains efficient and safe. Faults are natural fractures in the earth. Some faults are stable, while others may become sensitive when pressure changes. When we inject fluid, pore pressure increases. This can reduce effective stress, and may make a fault more likely to slip. If fault slip occurs, it can generate induced seismicity. This does not mean all underground projects are dangerous. It means geomechanical assessment is necessary. We need to understand fault location, stress state, pressure evolution, and safety margin. Coupled flow, geomechanics simulation helps identify where risk may increase and how to design safer operations. Reservoir simulation allows us to test underground behavior before taking expensive or risky field actions. Before drilling or injecting, we can build a geological model, define fluid and rock properties, create a numerical grid, simulate wells and operations, and forecast pressure, plume migration, storage performance, and risk. This is extremely valuable because real subsurface projects are costly and uncertain. Simulation helps us compare scenarios before implementation. In simple words, reservoir simulation lets us ask, what could happen underground if we choose this operation? That question is essential for safe energy storage. In hydrogen storage, the plume grows during injection and shrinks during withdrawal. But not all injected hydrogen may be recovered. Some hydrogen may remain trapped, mix with cushion gas, dissolve into brine, or move into less accessible regions. This affects recovery factor and deliverability. Simulation helps us visualize how the hydrogen plume evolves during cycles. It also helps forecast how much gas can be withdrawn at useful rates. For energy systems, deliverability is just as important as storage volume. A reservoir is useful only if it can return hydrogen when the grid or industry needs it. CO2 storage must be evaluated over long timescales. The project does not end when injection stops. The CO2 plume may continue to migrate slowly, pressure may dissipate, and trapping mechanisms may strengthen over time. We need to forecast behavior over decades to centuries. Simulation helps us track plume size, pressure footprint, caprock integrity, and long-term containment. It also helps design monitoring plans. A safe CO2 storage project must answer 3 questions. Where does the CO2 go? How does pressure evolve? And how do we verify that containment remains secure? Geothermal reservoirs are controlled by both fluid flow and heat transfer. Cold water injected into hot rock absorbs heat and moves toward the production well. Over time, the cooling front advances. If the cooling front reaches the production well too early, produced temperature declines. This is called thermal breakthrough. Simulation helps predict when thermal breakthrough may occur. It also helps optimize well spacing, injection temperature, production rate, and reservoir management. For geothermal energy, the goal is not only to produce heat today, but to produce heat sustainably over many years. Subsurface forecasts are uncertain because geology is uncertain. Permeability, porosity, faults, boundaries, and fluid properties are never perfectly known. Therefore, we should not rely on one single forecast. Instead, we should evaluate ranges of outcomes, such as low case, base case, and high case. These are often called P10, P50, and P90 scenarios. This gives decision makers a better understanding of risk and robustness. A good design should not work only in the best case. It should remain safe and useful across many possible geological conditions. A digital twin is a living model of the underground system. First, sensors measure field data, such as pressure, flow rate, deformation, and seismic response. Second, the model is updated using the new data. Third, the digital twin forecasts future scenarios. Fourth, optimization tools recommend better decisions. Finally, operators act in the field. Then the cycle repeats. This loop is powerful because it reduces uncertainty over time. Instead of using a fixed model forever, the system learns from monitoring data and becomes more reliable. Full physics reservoir simulation can be accurate, but it can also be slow. If we need to test thousands of scenarios, running a full simulator every time may be impractical. AI surrogate models solve this problem by learning from many simulation runs. Once trained, they can rapidly predict pressure, plume behavior, storage performance, or operational risk. This is very useful for screening, uncertainty analysis, and optimization. Instead of waiting hours or days for many simulations, AI can provide fast estimates. However, the AI model must be trained carefully and validated against trusted physics-based simulations. Physics-based models and AI models have different strengths. Physics-based simulators are built on conservation laws and physical equations. They are interpretable and trusted for critical predictions, but they can be computationally expensive. AI models are fast after training and can evaluate many scenarios quickly, but they depend on the quality and coverage of training data. If the AI sees a situation far outside its training range, it may give unreliable results. So the best question is not physics or AI. The better question is, when should we use each, and how can we combine them intelligently? A hybrid workflow combines trusted physics and fast AI. First, we build geological models and run physics-based simulations. These simulations generate reliable data and reveal key processes. Then AI models learn patterns from these data. After that, AI can rapidly screen thousands of possible scenarios. Finally, the most important cases are checked again with full physics simulation and field data. This workflow gives us speed, accuracy, and engineering trust. It is especially powerful for underground energy systems because we need both fast decision-making and high safety confidence. Optimization turns simulation into a decision engine. Instead of only asking, what happens if we inject here? We ask, what is the best design? We can optimize well placement, injection rate, storage capacity, cost, pressure risk, and safety margins. But real optimization is not about finding one perfect number. It is about balancing trade-offs. For example, one design may store more hydrogen but create higher pressure risk. Another design may be safer but more expensive. Optimization helps compare these trade-offs and select robust designs. Now, let us imagine an AI data center connected to renewable energy and underground storage. During the day, solar and wind generate surplus electricity. That electricity can be used to produce hydrogen. The hydrogen is injected underground and stored. At night, when AI demand remains high, but solar power disappears, hydrogen can be withdrawn and converted back to electricity. This creates a 24/7 energy support system for data centers. The key idea is that underground storage can help stabilize clean energy supply for digital infrastructure. A renewable hydrogen hub connects several components: wind, solar, electrolysis, compression, injection wells, underground storage, and end users. Excess renewable electricity is converted into hydrogen. The hydrogen is compressed and injected underground. It can be stored for weeks, months, or even seasons. Later, it can supply industry, power generation, transport, or grid balancing. This is especially important where renewable energy is abundant, but demand varies strongly with time. Hydrogen hubs could become major infrastructure for future clean energy systems. Many industries are difficult to decarbonize completely. Cement, steel, chemicals, and heavy manufacturing may continue producing CO2 emissions. A CO2 negative or low carbon industrial zone combines carbon capture, geological CO2 storage, low carbon hydrogen, and geothermal energy. CO2 is captured and stored underground. Hydrogen provides clean fuel or feedstock. Geothermal energy supplies low carbon heat and power. This creates an integrated industrial energy system. Instead of treating CO2 storage, hydrogen, and geothermal as separate projects, we could design them as one coordinated decarbonization strategy. This topic is highly relevant for Japan and Asia. Many countries in Asia have strong energy demand, limited domestic fossil resources, large industrial clusters, and growing data center infrastructure. Island grids and coastal industrial zones also need flexible and secure energy systems. Underground energy options can support energy security, emissions reduction, and industrial competitiveness. But regional geology matters. Not every location is suitable for hydrogen storage, CO2 storage, or geothermal development. Simulation-guided planning can help identify where underground projects are technically feasible, safe, and valuable. The future may not be one isolated storage project. It may be a network. Hydrogen storage hubs, CO2 storage hubs, geothermal hubs, renewable energy sites, industrial clusters, and data centers can be linked through shared infrastructure and digital monitoring. A digital twin control center can coordinate operations, monitor safety, forecast demand, and optimize energy flows. This creates a new vision. The underground as part of a smart energy network. The deep earth becomes not only a storage space, but a flexible infrastructure layer for clean energy and digital society. Let us finish with the main message. AI growth, clean electricity, and long-duration storage are becoming one connected challenge. Surface systems alone may not provide all the flexibility we need. The underground offers scale, resilience, and climate value. Hydrogen storage can support long-duration clean energy. CO2 storage can reduce emissions. Geothermal reservoirs can provide heat and power. Reservoir simulation and AI digital twins can make these systems safer, smarter, and more useful. So the future of AI is not only in chips, data, and algorithms. It may also depend on the deep earth beneath our feet. Thank you for watching.